Today video we will implement incremental conductance MPPT algorithm for a SEPIC converter based battery charging system in MATLAB Simulink. So before this I already uploaded two important videos. First one, how to design a SEPIC converter in MATLAB, where I explained the complete operation of SEPIC converter, how the circuit behaves during switch on and switch off states, how SEPIC can work as both a buck and boost converter depending on input and output condition, then complete design and calculation of inductors, capacitors, switching selections, then ripple analysis and more. Then second one, how to implement the INC MPPT algorithm for any DC to DC converter. So I explained about understanding of dI, dV and slope comparison, then duty cycle, then PW integration in MATLAB Simulink. So both links are provided in the description below. Make sure to check them out. The entire Simulink system consists of 4 main parts, and I will explain each block clearly before moving into the INC MPPT integration. So the 4 parts are PV panel, second one battery, third one SEPIC converter, then fourth one is incremental conductance MPPT algorithm. We move to PV source. First I will explain the PV module used in my system. Here I choose Solar 250 watts panel, which is a commonly used model in a renewable energy projects. I have chosen that 250 watts panel. This is a inbuilt system model. So the maximum power will get nearly 250 watts for a single panel. The number of cells per module is equal to 6. Open circuit voltage is equal to 37.3. Then short circuit current 8.78. Therefore, I introduce a constant temperature with a different irradiance level. We introduce the irradiance 1000, then 800, 600. Two parallel strings and two series connected module per strings, we will get nearly is equal to 1000 watts at the voltage of 60.2. Similarly, for 800 irradiance level, we will get nearly 807 watts at the voltage of 60.68. For 600 irradiance level, we will get nearly 609 watts at the voltage of 60.952 volt. Here the temperature is kept constant 25 degrees Celsius. So we can clearly see how the output power drops when the irradiance decreases. We move to battery. So after the PV panel, we move on the battery block because our target is battery charging. Here I choose the lead acid battery. The nominal voltage is equal to 48 voltage, rated capacity 200 amperes per hour, then state of charges I chose 45, then battery response is equal to 1. You can see that the open circuit voltage is nearly is equal to 73.8, approximately we will take 75 volt. The battery response is nearly is equal to 48 volt. Therefore, the output voltage is lower than the input voltage. That's what we introduce SEPIC converter to reduce the input voltage to the battery side. We move to SEPIC converter. It includes two inductors, two capacitance, and one switch, one diode. I already posted how to design a SEPIC converter in MATLAB. I have attached that video in description. You can check that. So based on the input voltage and the output voltage, we design the L1, C1, L2, C2 value. Here the capacitor is connected parallel to the PV panel and also SEPIC converter to smooth the input voltage to the battery side. After that, I already explained how INC MPPT works by comparing instantaneous conductance IBV and incremental conductance DI divided by dV. The key principle is at maximum power point, dI divided by dV is equal to minus I by V. We already discussed about that condition. Then left of MPP, the dI divided by dV is greater than minus I by V, the increasing the duty cycle. Similarly, the right of the MPP, dI divided by dV less than minus I by V, it reduces the duty cycle. So compared to the PNO, INC gives better performance during the sudden irradiance changes, making it ideal for a PV and renewable applications. Then after that, this INC is connected to the PWM generator DC to DC. Then we will set the switching frequency F as here. Let's run the coding. So based on the input and output, we design the SEPIC converter. From the workspace, all the values are updated in the model. So L1, L2, C1, C2. Let us simulate the model. You can observe that the maximum power of PV panel is reached at a very early stage due to the INC MPPT algorithm, and the corresponding gate pulses are generated for the SEPIC converter. The maximum power delivered to the battery is approximately it is equal to 925 watts. So this is the PV panel characteristics, and this one battery response. So the negative current is indicate that currently the battery is charging, therefore we are getting negative power. At time period of 0.4 second, we introduce irradiation is equal to 800, and 0.6 second the irradiation level is 0. At 0.8 second the irradiance level is 1000. You observe that input level under different irradiation condition, the maximum power for the time period of 0 second 1000, for the irradiance level 1000 we are getting 1000, and for 1000 and for 0.4 second the irradiance level is equal to 600. At 0.4 second the irradiance level is equal to 800. We are getting the maximum power approximately it is equal to 810. At time period of 0.6 second the irradiance level is 0. Then once again at time period of 0.8 second the irradiance level is increased to 1000. We are getting the maximum power characteristics of PV panel, and this one battery response. So let us compare PV curve as well as the battery response. At 0.6 to 0.8 second the irradiance level is 0. At the time the battery is at nominal, therefore it will not be charged. At 0.4 second the irradiance level is 800. We are getting the maximum 764 watts, and once again at time period of 0 second the battery power is reaches to 0. At the time the current is equal to 0. So this is the response of SOC, and this is the response of battery curve, this is the response of battery current, and this is the response of battery voltage. If you found this tutorial is helpful, please like this video and subscribe to the channel for more MATLAB Simulink and power electronics projects. Thank you for watching.